Okay, thank you. This is the last talk. I hope it will not be too boring for you. I will talk about decadal prediction. That's some work that we have done in the framework of the CECIL project, which you have been mentioned in some of the talks today. I have tried to put it in the general decadal prediction context, which has been set up for the CMIP 5 experiments, which this experiment is done to prepare the next IPCC report. So my talk will be in three parts. One about generalities about the decadal predictability, and why we should look and focus particularly on North Atlantic in the second part. And at the end, I will show you some results about, I would say, actual or real predictions, and that's a part of the results that will be presented in the IPCC report. I hope you like this picture. It has been shown many times today. Actually, this picture shows that this is the mean sea level, the latest version that is present on the Aviso site in Toulouse. And actually, the mean sea level as observed from satellite altimetry for almost 2 decades doesn't show very much decadal variability. Apart from the general trend of 3 and something millimeter per year, is mostly at the interannual timescales. But if we look at the regional trends, this one also you have seen it very, very often today. There are lots of patterns that are linked to decadal variability. For example, if we look at the Pacific Ocean, this shape, this shape here, and especially these patterns positive here, and the shape of this is very much like the same pattern in sea surface temperature of the Pacific decadal oscillation. So and this oscillation has a very important decadal variability. So we would expect that this is due to some decadal variability. In the Atlantic, same kind of things. You can see that there is this kind of tripole pattern, positive, negative, positive, which it's the opposite sign here, but it's something that is very much linked to the imprint of the winter North Atlantic oscillation on the ocean. This winter imprints very strongly the thermal structure of the ocean, even at depth, and so it can be anticipated that the sea level has some imprint of this signal. And if you look at the Antarctic circumpolar region, you can see this succession of negative, positive anomalies. This could be linked to the Antarctic circumpolar wave that has been evidenced by these authors more than 15 years ago. And the question here is there some predictability associated with these patterns? So I will enter the subject by saying a few words about decadal predictability in a model's words, because it is not easy to do it with observations, as it will be explained later. So if you imagine that you have a climate variable that is simulated by some models over a period sufficiently long to be able to compute decadal deviations from the long-term average, you are able to compute the variance of this decadal signal. And in addition, if you imagine that you have several simulations of the same period using the same models, but starting from slightly different initial conditions or slightly different parameters in the model or whatever, you can imagine that you are able to compute the variance of this decadal signal across the different members of your ensemble of simulations. And comparing the variance along the time and across the members is a way of evaluating the predictability. To illustrate this, we would like, it's easy to intuitively deduce that there is more predictability in a situation like this one than in a situation like this one. And this is the variance analysis that I presented is a way to put numbers on this kind of idea. So this has been done several times with lots of models, and including ensembles of model simulations where the models are different at each time. And for example, this paper by George Bauer shows the results, and it shows the fraction of variance that can be predictable, the variance of the signal that can be predictable using this kind of analysis. And as you can see, there is some places where the predictability is more important than in others, and especially in the North Atlantic. I'll come back later on that. Another way of looking at that is to see, for example, at the projections that have been shown earlier, for example, in David's talk, and to try to separate to analyze the causes for the spread of this kind of projections in the future. This has been done by Hawkins and Sutton, and they have split the uncertainty associated with such projections in three different kinds, one due to the internal variability, one to the model uncertainty by taking several models, and one due to the scenario uncertainty. And if you look at one given time and you look at the fraction of uncertainty from these different origins, you have this kind of things. If you look at global, like for example, temperature, global variables, you have a lot of uncertainty which is due to model and due to scenario at the end of the century after 80 years. But in the decadal time scales, it is not necessarily the case. You have still some contribution of the initial conditions, or I mean internal variability is somewhat something due to the initial conditions. If you look more regionally, for example, this paper was done by British people, so they are looking at the British eyes. It is even more important. You have a large fraction of the uncertainty which is due to the initial conditions. So from models, there is some predictability, and the place where there is the most predictability seems to be the North Atlantic. And by the way, this can be only done by models. You can't imagine that you can have an ensemble of observations. It would be needed to have several planets, and it's not possible. And the sources of predictability at regional and decadal scales are due from a large part to initial conditions, but the external forcing and the radiative forcing can play a role also. So let's focus now to the North Atlantic, again in a model's world. We won't talk about observation there again, and the North Atlantic is a place, again, this pattern of high decadal predictability, and the North Atlantic is a place of this meridional overturning circulation where the Gulf Stream transports heat and salt at the north. And if you look at the zonal average of the currents, vertical and northward, you have something like this. This is an overturning circulation function or a stream function and you show that there is a net transport in the surface and a net transport towards the north and a net transport towards the equator at depth in the ocean. And the intensity of this function measures the intensity of the transport in both branches. So there has been a few papers looking at the correspondence between sea level and the meridional overturning circulation. For example, in this paper by Balmaceda, actually it's a model. It's a model with reanalysis, so it's not fully a model, but you can see that there is strong link between both of them. Although at the very large, at the very slow time scale, the trend seems to be of the opposite sign. We have tried to look at that in the CNRM CM5 model that was presented by David this afternoon. And what we have tried to see is that over a very long 300-year-long integration of the model, there are some periods where this correspondence seems to be valid, and there are some shifts in the Atlantic meridional overturning circulation, and some times where this is not valid anymore. So there is probably some model dependence in this kind of relation between the MOC and the sea level, and also it seems not to be stationary. A way to look at the mechanisms in the North Atlantic is to perform housing experiments, such as the one that has been presented at the end of his talk by Detlef Stammer this morning. And this is what he did. I'll show again what he did. So you put some freshwater flux constant after one given date, and in that case, it is a quarter of a tenth of the sphere drop. And it can be a benchmark for characterizing the mechanisms that are important in the region. And the impact of that is, for example, in that case, this is the sea level response as a function of time in different ocean basins, and the North Atlantic is in black here. And this is the sea level patterns after 4 decades or so. We have tried to replicate this experiment in our model, and instead of having one single experiment, we've had 2 5 members experiment, one for the control experiment and one for the perturbation. And we found the results are presented the same way. So here is the impact in the Atlantic with the dispersion of the ensemble around. I don't think you see this very well, but this is significative. And this is not the case for what happens in the other basins. So we could say that even for this experiment, the impact is mostly localized in the North Atlantic. We have the other difference with the paper by Stammer is that our response is not monotonic. There seems to be some decadal modulation of the sea level rise in the North Atlantic, which is due to some mechanisms that we are investigating in a paper in preparation. There has been a similar experiment that has been conducted by Didier Swensjo, not far from here, using 6 different models. And you can see here that the impact of a housing experiment, which is 4 times what we had, he took 0.1 sphere drop as a forcing, as a freshwater forcing around Greenland. And what you see is that every model seems to have the same response, different in intensity, which is the slowdown of the meridional overturning cell. And to answer one question that was asked 2 talks before, I guess. So this is the impact of, this could be the impact of the Greenland melting. This doesn't mean, so there will be a slowdown of the meridional overturning cell, but this is not the meaning that the Gulf Stream will disappear. The meridional overturning cell could be reduced very drastically, but after 2 or 3 300 years, but the Gulf Stream will never disappear because it is driven by the, roughly speaking, by the Earth's rotation. So you see here the sea level impact for 4 of the 6 models, and you can see that there is a large variability of response of these models. So the link between the meridional overturning cell and the sea level has been investigated in model, reanalysis, and so on, but there seems to be some dependence on the model and potential non-stationarity. And the Rogel experiment can be a suitable benchmark for characterizing the mechanisms that are important there. So now comes the most difficult part, confronting models to real world and to real observations, and that was something that was asked for the decadal part of the CMIP5 experiment. And first of all, you need to have some knowledge of the past, for example, over the 50 or 60 last years. And here is what you have as a kind of information to constrain the reanalysis, which is a way of mixing data and models to have the best possible, in some sense, estimate of the reality. And you can see that there is a large variability of observation systems that last and disappear and rise, and that you can see that this kind of, for example, here you can see the number of observations at depths over, I don't remember, since the years 1980 here until the Argo era. So you can see that there is a dramatic increase in the observation, but there are also some decadal observing systems that could have some, as a result, some decadal signals in the reanalysis, and we need to analyze this carefully. For example, this is well known that it was discovered in 2008 that the data, mostly automatic expandable thermometers that fell into the ocean, had some problems in the 70s and until the beginning of the 80s, and this this is the average temperature of the 300 meters, which can be seen somewhat as a proxy for sea level, and this decadal bump of variability is now known to be wrong. So once we have an estimate of what happened, we can build sets of retrospective forecasts. This is, for example, here we have an initial condition. We run a set of forecasts for 10 years, and we can compare these with some uninitialized, which are the classical simulations of the 21st century. What about the Atlantic meridional overturning cell predictions? Oh, first, the reanalysis. Here is a set of different reanalyses that have been used to initialize the decadal predictions. You can see that there is a large variability of behaviors in the models. But if you somewhat normalize the signal, there is some common signal that is an increase in the MOC until the end of the 90s and a decrease after that. If you have, this, as I said, these have been used to initialize forecasts, which are shown here. And if you look at the scores of the prediction based on anomaly correlation coefficient, with the higher, the better the prediction is, you can see that the initialized predictions, this one, sorry, have more skill than the uninitialized predictions up to year 1 to 5 or 1 to 5. Unfortunately, the models have systematic errors and then have systematic forecast drifts. And we have at CERFACS tried to use this to hindcast sea level, and we have to deal with these trends. And here is a schematic of how we did. So if we want, for example, to forecast the trend, the sea level trend in the decade to come, and if we have a set of retrospective forecasts here, and here is the retrospective reanalysis, and here are the retrospective forecasts, you have no reason why the model will have exactly the same drift on average, same trend on average as the model. So you are obliged to face a forecast trend that is different from the observations. So you can compute the mean trend, which is in black here, and you can look at each forecast whether it is above the mean trend both in the forecast and in the observation. And since we have ensembles of forecasts, we can see how much of the forecasts are above the mean trend of the model, and compare whether this appears in the observations. So this is the basis for probabilistic prediction. So you have to count the number of cases where your event that you want to predict is present in the forecast. In the case the event is the regional sea level trend is higher than the long-term average global mean sea level. And you can compute this kind of probabilistic forecast maps. This is based on uninitialized experiments, and this is based on initialized experiments for example, the 2005-2015 decade. So the question is there one reason to believe one map than the other? Is there one meaning of these maps? So this is the reliability estimates, and this is the advantage of using this probabilistic estimate. So you just compute some quadratic error in the terms of probabilistics by taking the difference of the forecast probability of the events minus the observation, which is either 0 or 1, whether the event occurs in reality. And in the case that I show here, the reality is the reanalysis we have not taken. We could have, for example, taken some reconstructions or something else. This is a skill score. The score in itself has no meaning, so we need to compare it to some simple forecast system. For example, the climatological probability forecast. In that case, it means the probability forecast is always half. Okay, I'm almost done. So the forecast performance, unfortunately, are not significant at all in that case. However, so the skills are always negative. However, the advantage of using these probabilistic forecasts is that we can use there is a probabilistic framework behind this kind of score, and we can use not only the forecast itself, but we can use a set of other forecasts that has been made in the past. And this is shown here. The knowledge of all hindcasts except the current one helps us to calibrate the forecasts and to build a calibration curve, for example, of the forecast probabilities. And after calibration, we can have some positive skill score that again seem to be significantly higher than 0. It means the forecast brings some information up to lead time 5 to 6. I conclude here. So there is some potential for decadal prediction, especially in the North Atlantic. The realistic prediction experiments, whether it is for AMOC, temperature, sea level, there has been a lot of diagnoses that have been done on the CMIP5 database, show that the additional skill that is brought by ocean initialization is a positive up to year 5, and that after that There is no additional information brought by the ocean initialization. Uninitialized experiments can do the same. So we also need more work to investigate the mechanisms, especially in the North Atlantic, and lots of details of these kind of studies will be given in the chapter 11 of the AR5 that is currently, I guess, under review. That's all. Thank you.